Hello, everybody. My name is Brandt Bucher, and I'm here to inform you that Python is slow. But more than that, I'm here to inform you that a bunch of us are working hard to make it faster. So everything I'm going to present here today, this isn't necessarily super useful if you are writing Python code and trying to make it faster yourself, but basically it's just an interesting deep dive in a lot of the work that I and some others have been doing to improve the performance of Python for everybody, and how you can get involved if it seems interesting to you. So before we get started, a little bit about me. My name is Brandt Bucher. I started using Python about 7-8 years ago when I was an undergrad at UCI, and I fell in love with it. I found and fixed my first bug about a year after that, and I became a Python core developer during the pandemic. So adding structural pattern matching to the feature was my pandemic project. Stuck at home, nothing to do, might as well add features to Python, right? A couple years ago, I joined Microsoft's cpython performance engineering team, where I work now. And the first release that our team actually worked on was Python 3.11, which was 25% faster than 3.10. So I'm going to talk about some of that stuff. That's how we do that and how we've been building upon it as well. And the last couple of years, I've been working on creating a JIT compiler for CPython. So this may sound familiar to you if you've used languages like JavaScript or Java before. It's a lot of really cool, really interesting, really challenging stuff. And it's actually what we're working on in the back table there. So what is Microsoft's CPython performance engineering team? If you are hanging out in Python circles, you may have heard of us referred to as the Faster CPython project. Basically, we are a group of people who are working on Python from kind of all over different parts of the world. So we're here in the US as well as in Europe and Southeast Asia. A few of us are from Microsoft on the team that sort of started the initiative, but we work with a lot of people outside of our team. So for example, we collaborate with people at Snowflake and ARM, as well as undergrads at the National University of Singapore. And it's not like a closed group or anything. So if anything that I'm talking about today seems interesting to you, and this is something that you want to get involved in, come talk to me, because we'd love to have your help. So everything we do is out in the open. This is not like some super secret thing that is only benefiting Microsoft or whatever. Like, this is open source code, and we do all of our work out in the open. So if you want to see like kind of early stage ideas that we have for how to make Python faster in like upcoming releases, we have a public issue tracker here. This is where all of our kind of early ideas start and where all of our public discussion happens. So you can suggest ideas there. You can weigh in on existing ideas, or just kind of lurk and see like what we're up to. But just to kind of tease some of the results of our work, I already hinted at the 25% performance improvement in 3.11. Since then, we have been steadily making performance improvements on top of that. So we have one Python release per year, and each release since then has been around 5–10% faster. So cumulatively, that means that in the past less than 4 years, Python has gotten about 50% faster. Meaning your cloud bill is going down by 1/3, or you can do 50% more stuff just by upgrading. No code changes required, which is really, really cool. It's a big priority of ours to make sure that everything just keeps working the way it always has, and that you get all these transparent performance improvements for free. In terms of the benchmarks that we've been collecting, about 93% of our benchmarks have improved during that time. About half of them are over 50% faster. And a good chunk of them, about 15%, are over 100% faster, meaning they run twice as fast. And these aren't just tiny micro benchmarks. Like, this includes Pylint. So this is something that real people are running in CI constantly. So the same version of Pylint on 2 different versions of Python is now running twice as fast, which is really, really cool. So let's just do like a quick overview of like what Python is. Python is older than most people think. It's actually 34 years old. It just turned 34 on Thursday, I think. Right, Lakshmi? Right, 34 on Thursday, Python?
Yes.
Yeah. It is a very high level, very widely used, dynamic, interpreted, object-oriented language. So that means that like, it's not like a language like C where, you know, your variables are always an int or always a float or always a string or whatever. Like, you can do pretty much anything. You can monkey patch methods at runtime. You can unload and reload modules. You can change the types of local variables and do all sorts of crazy stuff. It's interpreted, which means that it's not compiled ahead of time. We're actually running your code dynamically at runtime. And it has automatic memory management and deep introspection and metaprogramming. So lots of powerful debugging features and cool kind of metaprogramming features. So if you look into this, like as a Python programmer, all these things seem great. These are the sort of things that have led to Python's success over the years because it allows you to do a lot of really cool things and not worry about the sort of stuff that makes programming less fun. But from a language implementer perspective, this is a nightmare because it's really, really hard to do all of this correctly, and doing it performantly seems basically impossible. Just to give you kind of a taste of this, like most objects in Python have arbitrary mappings of attributes. Every single object has a full dictionary attached to it, and you can put anything in there. It's not like just string keys. Like you can have just objects in the dictionary as keys. Bytecode, like the code that the interpreter is running, is an introspectable Python runtime object. People do inspect bytecode and change bytecode and create bytecode. So like even the deepest, darkest interpreter internals aren't off limits for people. Frames, again, a very low-level implementation detail of the interpreter, are runtime objects, and you can do crazy things with them in debuggers. And even like the most basic operations in other languages, like loading an attribute or storing a local variable, can run arbitrary code in Python. And simple operators, like addition, go through an incredibly complex double dispatching mechanism. So if you think you know how Python's addition operator works, come up to me, and if you can explain it correctly, I'll give you $1, because I guarantee you no one here actually knows how Python's addition operator works under the hood. And like I said, a debugger can be entered anywhere and do anything. And when I say anything, I mean anything. I mean changing local variables from one line to the other. I mean jumping from one line to another. So changing the line number of a running frame is something that Python officially supports. Again, these are all things that if you are a user, this is great to have, because like you can do all of this fancy magical stuff. Like packages like PyTest wouldn't exist without all of this magic. But at the same time, like this is something that we need to support because everyone relies on it, and it's impossible to do it while actually remaining performant, or it seems impossible. So that's Python. What is cpython? So cpython is the reference implementation of Python. And it's the Python interpreter that basically everyone uses, to the point where I'm going to use Python and cpython interchangeably for the rest of this talk. There are other Python interpreters. Very few people use them. If you type Python in the command line, this is what you're running. It has reference counting to do its automatic memory management. This is an implementation detail, but people have come to rely on it over the years, which means that we can't change it. It has an incredibly rich ecosystem of third-party C extensions, like NumPy, if you've ever used that before, and it's maintained by a few dozen active core developers, most of which are volunteers. I'm very lucky in that I get paid to do this work, but for the most part, these are all just people who are doing this either as retirement projects or nights and weekends. And it's free and open source. You can go to GitHub right now, download it, clone it, change the code, like do whatever you want with it. It's all there. So let's talk about like optimizations in general and how they relate to Python. So let's just start simple. So if I have x equals foo, and then I print x, what does x print? Foo? Wrong, actually, because the user entered a debugging session and they set x to bar and then continued the program. So x is actually prints bar. But that was kind of a trick question. So assuming that the user didn't enter a debugging session, what does x print? No, it doesn't print foo because x was previously bound to some class that has a finalizer that will actually overwrite the locals of the calling frame. This is something that people actually do. So we cannot prove that x will be printed as foo. And there are all sorts of things like this. So like even non-Python specific things, like here I have a function that will set two attributes of its arguments, x and y, to be foo and bar, and then check to see if the attributes are the same. So like, you would think that it would be safe to remove these two lines right here, right? Well, as we already saw, Python's pretty dynamic. So like, let's say that you can prove that no one is going to enter a debugger. And let's say that you can prove that those attributes aren't previously bound to something that will execute a destructor and start overwriting stuff. And if you're looking at this, you're saying, oh, well, those are attribute assignments in Python. Like, those are magic as well. You could have some class that's like overrides setAttr and getAttr and does crazy things with them. Let's imagine that we can prove that that's not the case either. If, and only if, all of these conditions are true, can we remove those two lines? The answer is no. And the answer is kind of stupid. It's because x and y could be the same object. So if x and y are the same object, then these two lines actually execute. And that's actually a very difficult thing to prove, that x and y are not in fact the same object. And so that's why a lot of the optimizations that you tend to see happening ahead of time in a compiler in a language like C or C++ or Rust, in a dynamic language like Python or JavaScript, we actually need to do these optimizations at runtime because we just don't have the information necessary to do all of this stuff ahead of time. So if you've ever written a compiler before or taken a compiler's class or whatever, you'll know that like kind of the typical steps are you parse out your code into some sort of intermediate representation, you check the types on it, and then you optimize and compile based on those types. In Python, we don't have any types. So in dynamic languages, we replace this type checking step with a runtime profiling step. And so we actually wait to start optimizing your code until it's already running, because that's the only time when we actually have the information necessary to perform those optimizations. So to give you an example, we're just going to walk through how Python actually executes and optimizes this Fibonacci function I have here. It's a basic kind of iterative Fibonacci. I bind A and B to be 0 and 1, and then we loop a bunch of times and repeatedly add A and B together. So specifically, we're going to focus on this hot inner loop, because this is where your program is actually going to spend most of its time. So Python uses bytecode to execute your code. So bytecode is basically sort of like a high-level assembly language for the Python interpreter. So it breaks sort of your textual source code into like more granular operations. And Python uses a stack-based virtual machine, which means that the operations that we're doing, push and pop things off of a stack, I'll show the stack here on the right. So when we start executing this code, we start with an iterator on the stack. And the for-iter instruction is responsible for advancing the iterator and pushing the next value onto the stack. So if we're advancing over a range, the first value would be 0, the second would be 1, etc. Now, iteration in Python is actually a fairly complicated thing. Again, Python is a very dynamic language. You can iterate over all sorts of things. You can iterate over like lists or strings or generators or user classes that have their own crazy iteration stuff. But in most cases, you're not doing a lot of that crazy stuff. You're actually just iterating over something simple like a range object. And so this is where specialized bytecode comes in. Basically, while your program is running, we take these generic operations, and at runtime, we say, well, are we actually doing a very simple version of this operation instead? And if so, the bytecode will actually replace itself with a specialized version. So you can see here that my for-iter turned into for-iter range. So we don't actually need to obey the entire iteration protocol that Python has in order to advance this range iterator. We can instead do the much cheaper operation of checking that indeed I am iterating over a range object here, and then basically just incrementing an integer and pushing it to the stack, which is a lot cheaper than doing all that other stuff. The next few instructions are pretty straightforward. Basically, we store the result in the local variable underscore. Then we load 3 more local variables, B, A, and B again, pushing them to the stack. The binary op instruction is responsible for popping 2 items off the stack, adding them together, and then pushing the result to the stack. Again, as I mentioned before, addition in Python is actually a very complicated operation. There's a lot that happens there. You could be adding strings, you could be adding lists, you could be adding user classes, NumPy arrays, whatever. But this is a very common case of actually just adding 2 integers together, and that's something that we can do a lot more efficiently. So again, this operation at runtime will detect that it's operating on integers and specialize itself into binary op add int, which basically just has a couple of checks that are very cheap to check that we are indeed adding integers together, and then an inline fast path for actually adding those integers. And one thing that I want to emphasize is that this continues to happen over time. So back to the debugger example, let's say someone opens a debugger and overrides the A and B local variables to be strings now. If this happens, we don't want to crash or produce the incorrect result with our bytecode. So what we'll instead do is basically those checks to check that we are operating on integers will repeatedly fail. Basically, it'll keep going back to that slow generic path. And after that happens enough times, basically the instruction will re-specialize itself, in this case, into binary op add Unicode. So as your program changes over time, the code adapts with it, and you always have those fast paths there available to you. And transparently, this isn't something that you need to do. This is something the interpreter is just doing for you. But in this case, we're just adding integers, so we'll leave it as binary op add int. Finally, we store the 2 results in B and A, and jump backward will get us back to the top of the loop. And what's really cool here is you can see that after just one iteration through this loop, we now have inline fast paths for what used to be very expensive generic operations. And we're able to do it a lot more efficiently now. And these two specialized instructions are two of just dozens of specialized instructions that we already have. Adding them is actually quite straightforward, and we're adding new ones all the time. So if you write Python code and there's some code pattern that you feel like should be faster but isn't, talk to one of us and we'll help figure out like what exactly is happening there and if that's something that we can specialize more effectively. We're always adding more specializations, and like I said, if adding one seems interesting to you, like I could also show you how to do it yourself so that you can benefit every user of Python. But basically, this is how we got our speed up in 3.11, or a big part of how we got our speed up in 3.11. So moving beyond that, what have we been doing since then? Well, you'll notice that not only do we have like this much faster version of our hot inner loop, but we actually have profiling information now. We know that we're adding integers together. We know that we're iterating over a range object, and we can use that information for further optimizations. And so this is where micro ops come in. This is basically the process of taking these big instructions and breaking them down into smaller, more granular instructions so that we can optimize them. Basically, this step happens completely automatically. If you write a specialization, the translation to micro-ops happens for free, which is really, really cool. So basically, once we've found this hot loop and it's specialized, we walk over each of the instructions in turn and translate them into these micro-ops. Once this is done, we basically have a much more kind of explicit version of what we're doing here. So every single kind of step in each of the instructions is now its own micro-op that can be optimized more aggressively. So the reason we want to break it up into these smaller forms is so that we can remove parts that aren't needed, reorder parts, or maybe change part of a micro-op based on information that we have at runtime. And again, that's what we're doing at the back table there. Once we have this micro-op trace, it's not really much use if we just keep it the way it is. So we actually want to start optimizing this thing. We optimize it using a technique called abstract interpretation. Again, this is kind of getting into the weeds a little bit, but I think that it's a really interesting concept, and it allows us to do a lot of powerful things with very little effort. So abstract interpretation is basically executing each of the micro-ops one by one, but instead of executing them on real values, we're executing them on fake symbolic values. This allows us to basically track the types as they're flowing through the program so that we know that at any point what the program would be doing if it was working on like real values. And so by doing this, we can actually like prove certain invariants about the program. For instance, like once we're done abstract interpreting this particular trace of micro-ops, we now know that 3 of our local variables are proven to be ints. And we also know the relationships between them. We know that by the end of the loop, A holds the previous value of B, and B holds A plus B. And so this information is really useful when we want to actually optimize this trace now. For instance, you may have noticed that we have these check validity and set IP instructions that are kind of inserted between every single bytecode instruction. These are to protect against people changing stuff in debuggers, basically to make sure that our assumptions hold and that the world hasn't changed. But since we're only working with integers here, we know that these are well-behaved objects that aren't going to start debuggers or do any crazy stuff behind our backs. And so since we've proven that everything involved in this loop is an integer, we can actually remove most of those validity checks and instruction pointer updates. Similarly, you may have noticed that we still have a couple of type checks left inside of the loop. Basically, since we've proven that we can't escape this loop and that once we're inside of the loop, we're only going to be operating on integers. Basically, nothing is going to change into something other than an integer. We can actually take these checks and move them outside of the loop. So basically, we check once before the loop begins, and then once we're inside of the loop, there's no type checks happening anymore. Everything is completely statically typed, as if we were running in C, but this is faithful to Python semantics. And so this idea of tracing hot paths through the code and then abstract interpreting, basically proving invariance of the program by sort of fake interpreting the program, is a really powerful technique, especially when they're applied together. So to give you another example, let's say I have my fizzbuzz function here. So basically, we loop over a bunch of numbers. If a number is divisible by 3, we print fizz. If it's divisible by 5, we print buzz. Divisible by 15, we print fizzbuzz. Otherwise, we just print the number itself. My implementation isn't particularly efficient. It just kind of works. Let's see what our JIT actually does when it starts executing that. So basically the first path to warm up through this loop is the case where nothing, neither 3 nor 5 divide our number. So basically the path where we just want to print the number itself is the most common one. So when we collect our trace for this loop, basically this path through the program, it looks something like this. And obviously we need fallbacks for the case where like the number is divisible by 3 or 5 so that we can fall back to the slow generic interpreter. But basically, once we have this trace, we can observe based on abstract interpretation and see that S is always going to be the empty string here. And we don't actually need it. So we can optimize it, and we end up with something like this. And we can continue doing that. The next path that's going to heat up is the one where we can divide by 3. And if that's the case, then similarly, we can prove that S is always going to be the string fizz and optimize appropriately. The next path is going to be the one where we divide by 5. We can optimize that one as well, and so on and so forth until every single path through our loop has warmed up and we've JIT compiled each one. And again, this abstract interpretation, by only considering one path through the loop at a time, is able to prove things, and we end up with actually a version of our program that is much more efficient because we were able to remove S and all of the string addition and Boolean checks entirely. And so once we have these micro-op traces, here's where just-in-time compilation comes in. Basically, it's not enough just to have these optimized bytecodes. We actually want to take them and compile them all the way to machine code, because what we have right now is statically typed, and we want to remove kind of any remaining overhead. So we have a couple of technical goals. The technical goals. Basically, we want to compile everything to optimize machine code, as I said, to remove their interpretive overhead. But we have a couple of like realistic goals to sort of keep us in check. So as I said, we need broad platform support. Python is a very popular programming language and it runs in lots of places, and it would be a shame if our JIT only worked on 1 or 2 platforms or for one architecture, right? Like, it should be able to work everywhere that we support Python working. Similarly, it should have few runtime dependencies. Right now, you can just download Python from python.org and everything works. You don't need to like install a C compiler or anything for things to get working. And finally, it should have low implementation complexity. As I mentioned, cpython is overwhelmingly maintained by volunteers, and so we don't want to have a super complicated JIT compiler that no one can understand and no one can fix bugs in and maintain and all of that. We want something that is able to be as automatic as the rest of the pipeline that I showed you today. And so that's where just-in-time compilation comes in, specifically a technique that came out a couple of years ago called copy and patch compilation. This is really cool. It comes out of a paper from Stanford. There's a link to the paper there. But if you don't like reading academic papers, I strongly recommend the blog post here on the second bullet. Basically, if you read that blog post, if you don't know how JITs work and you read that, you'll understand how JITs work. It's really well written, and it really emphasizes how good this approach is. But in a nutshell, it's a way of automatically turning an interpreter written in C, like the one that we have, into a fast JIT compiler. And it's really, really neat. Basically, just to give a quick rundown of how this works, here is sort of the C definition of one of those load fast instructions, which is responsible for loading a local variable. So there's kind of a few parts here. We basically get the value that we want off of the frame's locals. Then we increment the reference count so that our memory management is working correctly. And then finally, we push it to the stack. Now, normally, this instruction is going to be nested inside of a C switch statement. And that switch statement is going to be nested inside of a loop. And so this is basically how an interpreter works, is we loop over the bytecode and call one of these handlers for each one. However, what copy and patch does is says, instead of putting that in an interpreter, let's take it and put it in its own function and compile that function. And so when we're compiling the Python interpreter itself, before we start running your code, we actually are able to compile all of these small functions and get the machine code that we want out of them without needing to write any machine code ourselves. Basically, when the compiler compiles our tiny load fast function, in blue here, we have all of the bytes that we need to basically JIT at runtime in order to compile a load fast instruction. And the compiler even tells us where we need to like insert data, like, for example, an operand into the machine code as well. So we can parse this all out, and as part of building the Python interpreter itself, basically generate all of these functions in order to JIT each of the different bytecode instructions. So again, if you just do the work of adding a new specialized instruction to the base interpreter, all of this happens for free, where basically we're able to collect the hot traces, we're able to optimize them, and then we're able to JIT them without you needing to know anything about machine code. And like, I don't think this can be understated. It works everywhere because we're using another compiler. We don't need to like worry about how to compile stuff ourselves. So in addition to working on like all of the platforms that we care about for x86-64, it also supports 32-bit Windows and 64-bit ARM on all of those same platforms. So basically everywhere that people are realistically using Python, our JIT compiler will work with like so little effort, which is awesome. And so I know I went over a lot today, but this is just kind of one aspect. Like, I've been personally working on the tracing and abstract interpretation and the JIT compiler, so that's kind of where most of my knowledge lies. But our team is kind of taking a holistic approach to improving Python performance, and so there are lots of other areas that we've been improving things as well. So if you are looking to get involved or kind of learn more about what we're doing, we're always looking for better benchmarks. We have a benchmark suite, but some of them are quite old and don't necessarily represent what people are using Python for these days. So if you have some Python workload that you want us to make faster for you, turn it into a benchmark and give it to us. And a year later, your code will run faster. It's basically my team working to make your code run faster for free. I would definitely take us up on this. We still do lots of reference counting, which is kind of an expensive operation to be doing all over the place. So we're always looking for ways to reduce that reference counting overhead by, for example, proving that things can't be freed or other kind of interesting compiler optimizations like that. We're always trying to improve the object model. I know I mentioned before that like Python frames are runtime objects. Well, actually, now they're only Python objects if you ask for them. So if you don't ask for the Python object for a frame, we don't actually create one, which is a huge savings. Similarly, every object in Python has a dictionary attached to it. Well, not really. We only create it if you ask for it, and we use a more efficient storage mechanism under the hood if you don't. So there's lots of these little things where things that people have taken for granted in the Python interpreter, well, like most people aren't actually using these super dynamic, super low-level features, and so we can optimize for the case where they're not used. Inlining of functions is always an interesting one. Garbage collection improvements. I think in our benchmarks, we spend about 10% of our time in the garbage collector. So if you can make the garbage collector 10% faster, that makes all of Python 1% faster. Right? And then improvements to how we're treating things like integers and floating point values. These are still full Python objects. We're hoping to do something similar to what we did with frames, for instance, where basically if all you're using an integer for it is as an integer, then we can store it the same as like a C integer rather than having to have like a full object that's representing some integer value. And finally, concurrency and parallelism are always things that are interesting in Python. So Python hasn't supported true parallelism for some time now, but there's actually a team at Meta whose work is sort of related to ours. We're working on a lot of the same stuff, but we have slightly different goals, but we meet with them weekly. They're working on basically removing this thing called the global interpreter lock from Python, which will allow multiple threads to run truly concurrently, which is really exciting work, but it's also really difficult work as well, because there's lots of like locking and crashes and concurrency bugs and stuff under the hood in a project as old and complicated as ours. And that's not like a complete list. Like if you have ideas for how to make Python faster, or you have questions about why something in Python is slow, like I'm here. We also have that issue tracker that I linked to earlier. This is very much an open project. We've been lucky enough to have a lot of people helping us out and working with this. And if you want to make every Python process on the planet a little bit faster, this is a great way to make a huge impact and have a lot of fun doing it. So thank you for having me. I think Hack Night is super cool. I think Tech Night is super cool. So thanks for hosting it and putting all of this on. I'm at brandt bucher on GitHub and all of the Discords that all of you are on. And you can also email me at brandt@python.org. Thanks. And I don't think we have time for Q&A, but like I'm around, so just talk to me. Yeah.